is going to tell us about the search for a holographic dual for n heterotic strings. Do you need any R?
Yeah, I can't stand that. Can you sit down here?
So
Yes,
you can
yes,
sit on here. That's good. This will probably work fine.
Let's try again. Hello? Maybe if we put it here. Can you hear me? Okay, try. Can you hear me? Yeah, better. Okay, so it's have it here. So I'm going to get a warning. 256. Okay. Okay, I'm going to talk. What? I have 5 more minutes? Oh, that's what I get. Okay. So I'm going to talk about some work in progress with 2 of my students. Josh LePen and Aaron Simons. Aaron is just off to a postdoc at Brown, and it's going to be closely related to some other work which I will review on the way. One is an earlier collaboration I had with Doublecar a few years ago. We got stuck. I think we've gotten past where Atish and I got stuck a few years ago, but as you'll see, there's still it's still in progress, and there's still a number of things that we remain to do and haven't yet understood. Also, there was also addressing this same problem is a beautiful recent paper by Castro, Davis, Krauss, and Larson, actually part of a series of papers, and also coming from a slightly different angle, and also a paper by Givian and Kudasov coming from yet another angle. So here's an outline. I'm going to talk about what the question is. What the question is that I'm going to address. And then there's been a lot of recent discussion the last few years of the so-called small black holes, starting with work by Doublecar and the associated small black strings, and they enter into this in a very central way, and I'll discuss that. Then I'll discuss a supergravity analysis of the problem. And one thing we'll see from the supergravity analysis is that there's a very surprising appearance of W algebras. This is a specific kind of W algebra, sometimes called a nonlinear superconformal algebra. And then I'll turn to a heterotic worldsheet analysis of the problem and close with comments. And as I said a moment ago, this is work in progress. The problem is not sewn up, but already along the way, a number of interesting things have appeared. So what is the question? The question is, if we take Minkowski space, or some compactification of Minkowski space, we'll actually be interested in the latter, and we take n heterotic strings and put them on top of each other. There's a conformal field theory, 1 + 1 conformal field theory, that lives on those n heterotic strings. And so the question is, does that have a holographic dual? And if a holographic dual space-time, and if so, what is it? Now, in discussing this with people, this gets confusing, so let me say it once more. There are 2 heterotic string world sheets that come in this problem. First of all, we have n heterotic strings that are being stretched, and there's some conformal field theory that will have a charge proportional to n, 24n, 12n, that lives on there. But at the same time, this space-time that they live in, or the near-horizon geometry of the space-time, which is the string theory dual, has a worldsheet description as a world sheet of a heterotic string. So if this holographic duality exists, it relates a first quantized Hilbert space of n strings to a second quantized ordinary string Hilbert space where the world sheet is described by some conformal field theory that looks like ADS3 times some 7-dimensional spacetime. Now, so why should such a thing exist? Well, the first is that if we just take general Moldacina type scaling arguments, I mean, this probably isn't always exactly true, but if we take general Moldacina type scaling arguments, the near horizon geometry of any kind of defect in string theory should be dual to the low energy field theory that lives on the defect. And in this particular case, if we go to the dual type 1 picture, the heterotic string is a D1 brane, and so then this duality just becomes the usual open-closed duality, though that picture is not particularly useful because it becomes strongly coupled. And because the heterotic world sheet itself is a 1 plus 1 CFT, the dual spacetime will be expected to have some kind of ADS3 factor. So that's a very general reason we might expect such a thing. And a more specific reason is the surprising success of, in a series of papers, of which I'm about to explain, of the small black hole story of Doublecar, where he treated just the Doublecar-Harvey winding states, the BPS winding states of a string compactification as a black hole, and applied usual black hole type entropy arguments, and got a really, and later papers got a really surprising match between different quantities, and that really suggests that some dual of this type should exist, and maybe even implies it. It's hard to understand how this picture could have worked so well if there isn't a holographic dual lurking around. Now, this picture really only works in one dimension, and that is why in this talk I'm going to specialize to the case of T5. All right, so now let me now review some ancient facts from late 80s, early 90s, and that is the space-time supergravity solution. If you just take the leading low-energy supergravity and solve it with the heterotic string as a source. Here's the geometry that you find. You get 8 flat dimensions, and then you get the directions longitudinal to the string with some conformal factor in front of the geometry. That conformal factor depends on it's the radius in the 8 flat dimensions, so we can't, as far as the world sheet is concerned, we can't think of this as the product of two conformal field theories because this R is the radius in the transverse dimensions. And what exactly R is depends on what we're compactifying on. Here we're going to compactify on T5, and so R squared will just be the transverse, the R squared in the 3 dimensions, which means that we've got a 2-sphere factor here. In addition, the string coupling is going to 0 at the core of the string. So in this analysis, which according to in this analysis, there's a singularity at R equals 0, which according to the way people thought about things at the time, that seemed perfectly natural. There's a source sitting at R equals 0, so the supergravity equations should become singular. A few comments about this. First of all, obviously it's half BPS. In the heterotic string, we start out with 16 supersymmetries in flat space, so we break down to 8. Near the horizon, that is, well, of course it's not a horizon, it's really near a singularity. The radius goes to 0, the string coupling goes to 0, and the radius, well, R goes to 0, and the radius of this 2-sphere goes to 0. And that means that the curvature it's not flat space here. The curvature is becoming very large here, and alpha prime corrections are important, so we can't trust this supergravity solution at radii r that are less than n. And alpha prime corrections should be important. Now, since alpha prime corrections are important and the string coupling is getting small, this is a job for the string world sheet. In other words, we should look for, if we want to improve on this, this is exactly the kind of situation in which a string world sheet analysis would be important. Large alpha prime, weak string coupling. And what's even nicer is, unlike in many problems that we've encountered of this type, for example, if we want to understand a small ADS5, we want to understand ADS5 cross S5 with where n is 1 or 2, we don't have any Ramon-Ramon fields in this problem, so we don't have to worry about Ramon-Ramon conformal field theories. Now, I want to give a rather general argument about why the Doublecar-Harvey states. So now I'm going to turn to small black holes and talk about them a little, and we'll see why they are relevant. Well, first of all, what are the small black holes? Well, they exist in a compactification down to 4 dimensions on the 6 torus, and there are states that wind around a cycle of the torus and have both momentum and winding around that cycle, and they have a degeneracy that goes like e to the 2 pi times the square root of the momentum times the winding. Now, that's a pretty rapid growth of states at large n and w, but it's not rapid enough for the thing to become a macroscopic black hole. This is really it's really linear in the charge, and macroscopic black holes have an entropy. So this is the entropy. A macroscopic black hole would have an entropy that's going the square of the charge. But still, I think that it should be thought of as a black hole for the following reason. What is a black hole? Well, a black hole is something from which light can never escape in the classical limit. And in string theory, when we have a microscopic description of the black hole, the fact that light can't escape is a consequence of the second law of thermodynamics. So a black hole is something for which the entropy factors prevent any energy from escaping in the macroscopic h bar goes to 0 limit. Now, if we take a macroscopic black hole and look at how its entropy scales in the classical limit with the classical fields kept fixed, we find that the entropy goes like 1 over h bar. Here, it's going like 1 over the square root of h bar. But still, that's enough so that when h bar goes to 0, if we take the classical limit of one of these states, no finite amount of energy can escape without violating the second law of thermodynamics. Now, one of the beautiful things that we've learned in string theory is that microscopic violations of the second law of thermodynamics appear in space-time through, manifest themselves in the space-time picture in the form of event horizon. And since the second law of thermodynamics does prevent energy from escaping from one of these guys, we should expect the formation of some event horizon, but if we look at it a little closely, the size of that event horizon should be the string scale. And so we would like to think that in some sense in string theory, there is still an event horizon around these Doublecar-Harvey states, even if it's too small to be seen in classical supergravity. Okay, so now I want to briefly mention what the Doublecar and Doublecar, Denef, Moore, and Pioline did with these guys. Well, what they did was they mapped it to the dual 2A picture, and then these small black holes can be understood as some kind of wrapped M5 or NS5 branes in the 2A picture, and they're very general formulas for the entropy, and they found that when you specialize to the image, the dual image of the charges carried by a fundamental string, actually a fundamental heterotic string under this duality just maps to a wrapped NS5 brane, and you plug it into the entropy formula, lo and behold, you get exactly the right answer with the numerical coefficient. Actually, they found much more than this. They found there was a whole infinite series of corrections which matched here in a very beautiful and impressive way. And this was beautiful, but it was kind of surprising and a little bit fishy. And the reason it was fishy is that in this analysis, the leading term for the charges of heterotic string, the leading term vanishes. So everything, instead of being computing, ordinarily you would think of this term, which is giving the heterotic string entropy, as a subleading correction to the leading term. If you don't have the leading term there, we no longer have a macroscopic object. We can no longer use supergravity. R squared corrections, R to the fourth corrections, R to the sixth correction are all important. And the supergravity analysis on which the derivation of this formula is based all just breaks down. So that's why it's fishy. But on the other hand, it works so well, it's clear that they were doing something right, and that there's some reason you're allowed to forget about these terms. And one of the pieces that you would expect to be true is to suggest that there should be an actual black hole solution if you include alpha prime corrections. So that was the next thing that was done, and there was a series of papers on this in which one included R squared corrections and indeed found that when you include R squared corrections to the heterotic Lagrangian, you get you have some alpha prime corrected equations, and you find that instead of this Gibbons-Harvey Doublecar-Ruiz solution, which has a singularity at the origin, you in fact get a near horizon ADS2 cross S2 region. But let me just to say why we can't really trust this. I mean, if we do a field redefinition, there's no preferred form of the metric. And if we do a field redefinition and we have a new metric which differs from the old metric by an addition of the Ricci tensor times alpha prime, then it could take a non-singular geometry. So you could, for some coefficient here of order 1, it could change the size of this S2 from something finite to 0. So we really can't be sure what we're doing in supergravity, but still something looks right. And what we would really like to do here is to, we know now how to solve exact supergravity. In principle, exact supergravity solutions would include all R squared corrections. That's what world-sheet conformal field theory does. And, and in this case, we don't have to, as I said before, we don't have to worry about Ramon-Ramon fields. And also there's so much supersymmetry here that there isn't a lot of, it's not like trying to find an exact conformal field theory for a Calabi-Yau space. There's so much symmetry here that we should be able to find the conformal field theory in question. Now, I don't really want to talk about the 4D black holes. I really want to talk about their lift, because it's simpler to think about. So if you look at this near horizon geometry, what you have is a Kaluza-Klein U1. Because of the winding charge, it's fibered over the ADS2 cross S2, and in such a way that the total space, it's really just, the U1 is really fibered just over the ADS2, in such a way that this U1 fiber, the circle that the string is wrapped around, together with the ADS2, make an ADS3 times S2, and we can go to the cover of this, And we have an ADS 3 times S2, which would be the near horizon not of a wrapped, not of a Doublecar-Harvey winding state, but we're going to uncover that and get a near horizon of a black string in 5 dimensions. And really, I was just talking about 4 dimensions to make the connection with all that work that had been done on the small black holes, which was mostly in the 4-dimensional context. So from here on out, we're going to turn to the simpler problem of the near horizon geometry of a stretched heterotic string, which I started talking about in the introduction, in 5 dimensions. And now we can understand why it is that the case T5 is special, and we'll see later again another reason why T5 is special, and in fact we'll see that there doesn't seem to be any way that it could have worked in any other dimension except maybe 10. All right. Now, still we didn't, this problem of black strings in 5 dimensions has very recently been analyzed by Castro, Davis, Krauss, and Larson. And what did they do? Well, they just took the supersymmetry transformations for theories with 16 supercharges in 5 dimensions, and it turns out that rather recently those supersymmetry transformations, including the R-squared corrections, which somehow seem to be the important ones, have been worked out. And one of the very nice things that happens about it is that if you write the supergravity transformations in terms of the auxiliary fields, they don't even know about the R-squared corrections. The R-squared corrections really just affect the auxiliary field equations of motion. And what did they find? Well, they found exactly what we would hope for. There's a half BPS solution in 5 dimensions, which carries the charges of n Heterotic strings. The string coupling in the there's a near horizon ADS 3 times S2 region, and the string coupling is going like 1 over the number of strings. And so this, and furthermore, they show that both the left and the right central charges that you would associate by the corrected Brown-Hanot formula take the right values for this supergravity geometry to be the dual of the n heterotic strings. Okay, but now that we still would like to do better than that, and I would take this as further evidence that this, again, in 5 dimensions, just like in 4 dimensions, you have to be worried about just including R-squared corrections. Though it seems to be working, we'd like to do better, and we'd like to find the exact conformal field theory. And I'll come back to that in a bit. But already, just in supergravity, we come across a puzzle. The puzzle is, what is the near horizon superisometry group? Well, the first thing is that it must have 16 supersymmetries. Because we started out, the full solution that they write down has 8 supersymmetries, but we know that that can't be all, because once we get into the near horizon region, we have an isometry, the SL2R isometries, and since the Killing-Spinner equations commute with this isometry, we can generate 8 more supersymmetries by acting on the old 8 supersymmetries to give us a total of 16 supersymmetries. So we got to have at least 16 supersymmetries. Now, if you look in the tables of all the supergroups which contain obviously it has to contain SL2R, there's only 4 of them that have 16 supercharges and contain SL2R. There's only 4 of them, and what did I do? There are only 4 of them, and here they are. And I'm listing here, there are symmetry groups. So here's the puzzle. we have to have one of these 4 superisometry groups. But according to Brown and Henault, the isometry group or superisometry group of an ADS3 geometry always gets promoted to some kind of affine group. So the SL2R, for example, gets promoted to Virasoro algebra. And in the usual story, we would have 8 supersymmetries, and we would have SU11/2, and so we would get some kind of 5 minutes, n equals 4 superconformal algebra. The problem is that none of these guys have an affine extension. You look up the tables, and the biggest group that has an affine extension is the large n equals 4 superconformal algebra, and that has a global subgroup with only 8 supercharges, and doesn't contain any of these groups. And I want to emphasize that this puzzle doesn't really rely on any connection to string theory. It's already a puzzle just within supergravity, because these affine groups can be constructed a la Brown and Henault just from the asymptotic dynamics at infinity. Okay, so which group is it? Well, we did a brute computation, and I guess I'm going to hurry up a little bit because I've only got 5 minutes. We did a brute computation, and we find that you get OSP4 star 4, where the SU2 is the geometric SU2 of the 2-sphere that's sitting there, and the SP4 is SO5 is the spin frame rotation. It's the R-symmetry group. You can also think of it as the rotations of the spin frame in the 5 toroidal dimensions. Now, I can't help resist mentioning that if we had been on T4, we have to have at least an SO5. The other options were SO7 and SO8. And if we'd been on T4 or T3, there were no groups available, no supergroups available that made any sense. So just the group theory is telling us that T5 is special. There's one other thing that makes sense, and there is something with 16 supercharges that has an SO8 R-symmetry group, and that would naturally arise if there's some kind of S7 times ADS3 near horizon geometry of a heterotic string in 10 dimensions. Okay, so this is the puzzle that I mentioned. Now it turns out that while there are no ordinary superconformal algebras that contain OSP4 star 4, there's a special class of W algebras called nonlinear superconformal algebras that were discovered by Knižník and Bershadsky, and they contain, the highest spin field is 2, but the algebra is nonlinear. So the right-hand side of the commutator of 2 supercharges contains a product of 2 R-symmetry generators. And these groups have not had many applications in string theory or elsewhere, but they appear to be very special kinds of superconformal groups. But what's even more interesting is that there's a recent paper by Henault, well, not that recent, by Henault, Maus, and Schwimmer that analyzed what kind of boundary conditions can you have on ADS3, and they concluded that, in fact, you can have consistent boundary conditions where the asymptotic symmetry algebra is precisely this nonlinear. They have a very short table, and it includes this example, and you can have asymptotic symmetry algebra, this nonlinear superconformal algebra is an asymptotic symmetry algebra of ADS3. So things seem to be kind of fitting together. With the R-squared corrections, n-stretched heterotic strings can have this kind of near horizon geometry, and it would be consistent for them to have this nonlinear superconformal algebra as the asymptotic symmetry algebra. Okay, so not much is known about unitary representations of these algebras. So let me now move on to the issue of what is the world sheet CFT, and we do have a conjecture here, which I want to get to. So it's hard to get an S2. S3s are easy to get. They're just WZW, SU2 WZW models. S2 is harder to get. But it has come up before, and it came up before when trying to find the near-horizon geometry of the charged non-BPS black hole four-dimensional heterotic string theory, where the magnetic charge came from the left-moving current algebra, and so therefore it was non-BPS. And the way that worked, which took a very long time to figure out and was actually quite subtle, is you think of, you get an S3 in the following way. You start out with this S2. You start out with this S2, and on the left, you have a fiber from the current algebra. On the right, you bosonize the two superpartners of the two coordinates of the S2. They live in the tangent bundle, so the current is fibered over to that S2, and this whole thing is some kind of quotient of S3. And what we showed back in the early 90s was that this S2 carrying magnetic charge Q in the heterotic string was this rather bizarre asymmetric orbifold quotient of a level 2 Q squared minus 1 WZW model. And in that analysis, there was a surprise, which was that the conformal field theory did not become trivial when we set the charge to 0. We called this thing a neutral remnant. It was a black hole which carried no charge, but nevertheless had an infinite throat with a linear dilaton. And at that point, okay, my time's out, but I'm almost there. Yeah, at that point, this neutral remnant seemed to have no meaning in life, no purpose in life, but now maybe it does, because what I want to do now is to modify our old construction in two ways. I want to replace the T6 by a T5. I want to replace the linear dilaton with a 0, 1 SL2R WZW model with the appropriate central charge. And then this thing carries the charges of Q magnetic strings for general K, Q magnetic strings, and also n over 1 g squared heterotic strings. That's what the H flux on the ADS3 is telling you. It's telling you that there's some fundamental heterotic strings there. And if you work out the formula, n is going like 1 over g squared. And then, so for general K, this would be Q of these magnetic strings on top of n heterotic strings. But for the special case, K equals 2, what we call the neutral remnant, we would have just a heterotic string. So this is our proposal for the holographic dual represented as a exact worldsheet CFT of n heterotic strings. And the size here does not depend on the number of heterotic strings. The number of heterotic strings is related to the string coupling as we expect. Now, just some brief comments. There's a related conjecture in Givyon and Kutuzov. Also, Atish and I had some similar things, but some missing ingredients a few years ago. The proof of the pudding is if we can find the 16 spin fields. We haven't. Some very relevant and important literature is the old papers of Givyon, Kutuzov, and Cyborg, and Givyon and Pacman, where they describe in detail the lift from worldsheet to space-time Virasauros, which allows you to check the central charge of the space-time theory. It's a sort of stringy Brown-Hanot formula, but it's going to need to be modified for these nonlinear superconformal algebras, so we can't just copy formulas out of that paper. So conclusion is that several errors point to the existence of a dual to the heterotic string for n heterotic strings. There's several conjectures. It seems that they must have some kind of exotic W algebra as an asymptotic symmetry algebra, and there are more things that we need to sort out. So let me stop there.
Okay, there's time for one short question and one short answer. So who's going to ask the short question?
So,
Oh,
Andy,
yes.
the general reasons
Sorry.
you gave for expecting a conformal field theory would also be valid in other dimensions, not just for a T5 compactification, perhaps other, let's say, T4, T3 compactifications. Would you expect that there should be a conformal field theory in those cases too?
You want me to take your name off the argument? Is that what you're saying? I mean, I would have expected that, but you know, there must be some kind of glitch there because the supersymmetry algebras just don't exist. I mean, we were saved by the existence. It just so happens that in this list of 4 super isometry algebras, we were saved by the fact that one of them had an SO5 symmetry group, and there was a natural way for SO5 to arise. And if we'd been working 1 dimension higher, I don't see how it could have worked out. But maybe I'm missing something. Yeah. So.
But SO5 is not the symmetry of the worldsheet string theory, right?
It's not a symmetry.
Because you have a T5.
It's not a symmetry.
So it's a symmetry of supergravity, but not of the conformal field theory on a T5, right?
No, but you can. No, but already at the level of the supergravity, you can see that you needed. Yeah, I'm not arguing from the point of the worldsheet. No, this is just a statement not about which groups have affine extensions, but just from the superisometry group itself, right? Just from the supergravity analysis, if a string worldsheet has a macroscopic string worldsheet has a near horizon geometry, it always has to have, in a heterotic string, it always has to have 16 supercharges. In the type 2 string, it would have to have 32. You would expect 32 supercharges. So there has to be some supergroup that makes sense. And it doesn't seem like there is going to be one in every situation.
Okay.
Because there's only 4 supergroups. So you might get 4 situations. Actually, one thing I left out is that there's also, you could have also had, instead of 16, you could have had 14 supercharges. There's a G2. So my guess is that all those supergroups appear as near horizon superisometry groups of something in string theory in some context or another.
Okay. So we're going to go to the next one.
Yes.
Okay. Thank you. Thanks. So the next speaker is Jan de Boer.